Well, thank you for coming early. I know that being awake in the middle of the conference after 3 full days and in the morning is you're kind of half an undefined behavior yourself. So thank you all for being here. I'm going to talk about undefined behavior in C++. So we're going to talk about what it is, but also it's just as important to know what it's not. There is a lot of legend around undefined behavior, and we'll talk about the legend, we'll talk about the reality, and I hope to convince you that the reality is actually more scary than the legends in its own way. So the concept itself is in the standard. So here is an example. According to the standard, if the addition overflows, the result is undefined. The language, the program is not well defined. You can find that. The standard imposes no requirements on the results of this operation. And if you're jumping up and down to correct me right now, hold on, we'll get to that part. More importantly, the standard actually imposes no requirements on the result of the entire program that calls this function with an input that causes integer overflow. How can that be? Well, I'll show you. So here comes the legend. Since there are no requirements on the result of the entire program, the famous example is that it will make demons fly out of your nose. It can do terrible things to the state of the universe, format your hard drive, which may be even worse. Well, I find these legends not particularly helpful because after you encounter undefined behavior for the 100th time and the nuclear reactors still haven't melted down, you kind of get used to the idea that people are overstating it. So, I don't like over-exaggerating the dangers, and if you're advocating for eradicating undefined behavior in your own code base, I don't recommend basically repeating these legends again, because people basically can get scared only for so long if it doesn't happen. There is a real danger, which I will demonstrate to you and you can take with you and demonstrate to your peers, which is that the entire program becomes undefined if any of the operations in it exhibit undefined behavior. And undefined means the standard imposes no requirements on the result or on the behavior of the program. So let's see how that works. So there are several common ways to kind of understate undefined behavior. One is, okay, I have integer overflow. It's not defined what it does, but it does something. Whatever it does, the compiler will emit some instructions, the hardware will do whatever it does. That happens, and if I'm okay with whatever result it produces, then that's the extent of it. That's not true. So how can it be not true? Well, we're going to see. Okay, so here is the first example, and because it's a 30-minute talk, I'm not going to switch to the code to run it, but I have the code for all of this. If you want, after the talk, I'll run it. Come to me, talk to me. I'll run it in front of you, and you'll see what happens. So if we assume that the compiler can see the entire code, then the compiler in general will assume that undefined behavior does not happen. In particular, it means that when you call f, integer overflow does not happen, so I is not equal to int max. It will then, in that assumption, eliminate what is now basically dead code, because I is not equal to int max. So the first line of G is dead code. It will never happen. So G will never return false if the compiler does this elimination. Now, how can the compiler do that? Doesn't it change the observable behavior of your program? Well, yes, but not in a way that the standard prohibits. Because if undefined behavior does not happen, then the result is correct. You will return f of I. If undefined behavior does happen, it did change the behavior of your program, but the standard didn't say what the behavior of your program should be in the first place. So whatever the compiler did is acceptable. What do today's compiler actually do? I haven't found any compiler that would do this optimization all the way through, but they do half of it. So here is our first function, f of I. Signed integer overflow is undefined behavior according to the standard. Undefined behavior never happens in a correct program. And incorrect programs, well, the compiler doesn't care about incorrect programs. Therefore, it's perfectly valid to optimize this function to return true. Do the compilers do that? Let's find out. We can do it by direct proof. We can compare the assembly generated by the compiler from the function f, which is I plus 1 greater than I, or function g, which is return true. Both GCC and Clang, with optimization turned on, produce the assembly on the bottom. You don't need to know how to read x86 assembly to see that they're exactly the same. And if you do know how to read x86 assembly, it's returning 1, which is true. So yes, today's compilers will optimize the I plus 1 greater than I to return true. Now, are we sure that this is because of UB? We can find out. If we change signed int to unsigned int. For unsigned int, overflow is not UB, it's defined in the standard. What must happen, it will go back to 0. So now we can compare assembly of the signed I plus 1 greater than I versus unsigned I plus 1 greater than I, and you can see that the assembly is different. So yes, the optimization was done only because I is unsigned integer. Yeah, the one on the right compares I with int max. So it actually didn't do the add and greater. It figured out that the only way this can return false is if I is uint max. So the compiler did a slight transformation, but it still does the compare. Whereas on the left, that's a signed int. There is no transformation at all. It returns true because for signed int, I plus 1 is always greater than I. And if it's not, you get what you deserve. The entire program is undefined. Okay, well, so as I said, all compilers do that particular one. Well, all the ones I tried. You may have other examples of undefined behavior, and you will have people saying, well, I tried it. My compiler does something specific, and I'm okay with what it does. For now. So here is an example of something that actually did change. So here is a program, very simple. We print before, we go into an infinite loop, and we print after. Well, we should never print after, right? It's an infinite loop. GCC, prior to version 9, I believe, prints before and hangs forever. Clang, as far as I could go back, and GCC at least 10 and above, and I don't remember where exactly it changed, prints before, immediately prints after, and exits. So if you had that in your code and you upgraded the compilers, your behavior might change. And this is actually a good example to explain, why do they do this to us? It's not like we didn't have other problems programming in C++. Why on top of everything else they did that? Okay, so between 9 and 10 as the transition happened. Well, the compiler did that because the standard actually says that the program can do whatever it wants, because this is infinite loop with some qualifications that I won't go into, but this particular infinite loop is undefined behavior. Okay, why? Well, there are some obvious reasons. You need support for different kinds of hardware. On some hardware, certain things just cannot be done. Yeah, okay. On some implementations, you have no reasonable alternative, no way to define it. Okay, fine. But a very important reason is actually performance and optimizations. And this infinite loop is a perfect example to demonstrate. So here is some code. We go over it from j from 0 to n in steps of 2. And we increment n1, and then we increment n2. As it is written, we iterate over j, which means we incur the overhead of incrementing j and comparing with n twice. Notice that we don't actually do anything observable between, so it would be a very desirable optimization to collapse these two loops. And most compilers will do that for you. So they convert it to the code on the bottom, where in a single pass of the loop you increment both n1 and n2. Notice, however, that this is not a correct optimization. It's correct if the loop stops, which means if n was even. It's not correct if n was odd, because then we never exit from the first loop and we never increment n2 at all. The compiler cannot know whether the first loop terminates or not, but it's still a very desirable optimization. So the statement in the standard is that if the first loop does not terminate, it's undefined behavior. Therefore, the optimization now becomes valid, because if the first loop terminates, the result of the program is unchanged. N1 and N2 will both be incremented at the end. If the first loop does not stop, the result of the program can be whatever the compiler wants it to be, including the one where N1 and N2 are incremented both. So either way, the optimization is valid. Now, in truth, there are many other reasons for undefined behavior, and yes, people argue about whether this should be undefined behavior or not, and I will be the first to agree that in many cases there are things that you really want to do and you should be able to do, and the standard says, yeah, technically it's not UB. They're working on it, they're making it better. There is still a lot of work to do to clean it up, and a lot of the undefined behavior that was undefined due to hardware variety doesn't make sense today. They finally did the right shifts of integers in C++20. They made it always equal to division by 2. Thank you. But the big reason for remaining undefined behavior is still the optimizations. And the root cause is the compilers have to make assumptions that they cannot prove. In order to do many successful optimizations, why they cannot prove? Well, it could be because the data is runtime dependent, could be because something like it's halting whether the program stops or not. You just can't prove that in general. But the compilers have to make these assumptions anyway, so the standard says, assume that the assumption is true. If it's not, that's on the programmer. Now, there are several varieties of this, so not everything that the standard doesn't exactly specify is undefined behavior. Undefined behavior, if you encounter it, it means that the entire program is ill-formed. There is also unspecified behavior where the standard says one of the following things must occur, but we don't say which one. Any particular implementation will have to choose, and may choose differently in different cases. So the example is in which order the arguments of the function are evaluated. The standard doesn't say the order, but they must be evaluated one at a time in some order. It's unspecified, but not undefined. And the last one is implementation-defined behavior, where the standard doesn't say exactly what will happen, but includes a requirement that any conformant implementation must essentially amend the standard and document what it does. So on any particular implementation, it's well defined and must be documented, but it doesn't have to be documented in the same way. We're only going to talk about undefined behavior, the true undefined behavior. So here is the logic of undefined behavior used in program optimizations. First, assume that undefined behavior does not happen. Second, deduce the constraints on the state of the program. Third, assume that these constraints are always true because undefined behavior does not happen. And then simplify the code based on these assumptions. Why can we do this? Well, if undefined behavior indeed didn't happen, the results are correct because the assumptions hold true. If undefined behavior actually did happen at runtime, the results are also correct according to the standard because any result is correct. Okay, so here is an example of compilers actually doing this kind of reasoning. And now we're kind of getting to the point where I'm creeping up on that moment where I'm going to demonstrate how the entire program becomes ill-defined. So I have a function takes a pointer, increments whatever the pointer points to, and then has a return which is guarded against null. Now, again, pretty much every compiler today will drop that question colon. Why? Now, because the previous line where we unconditionally access star p would be undefined behavior. Dereferencing null pointer is undefined behavior. The standard doesn't say, by the way, it must crash. The standard says it's undefined behavior. There's hardware on which address 0 is perfectly valid. Still undefined behavior. So the previous line is undefined behavior if p is null. Therefore, we don't need to check for p in the return statement because we know that p is not null. And if it is, we're in undefined territory anyway, so anything goes. All right, what do the compilers actually do it? Yeah, you can benchmark this, but I prefer to always compare the assembler. On the left, assembler generated with the question colon. On the right, the same thing without question colon, just return star p. Again, you can see that they're absolutely identical. So yes, the compiler removed the question colon. Well, you might say the compiler didn't really taint the entire program because if p is null, it's going to crash at the ++ line, and therefore it'll never get to the return. So we're still, basically undefined behavior is still really confined to the place where it happens. Don't worry, it gets worse. Here is another one. Here is a guarded increment. So now I'm going to say, well, p might be null on input, so I'll only increment if p is not null. This line is entirely correct. It should never crash in any case, assuming dereferencing null pointer crashes on our platform. This should never crash. But on the next line, I just go return star p. The compiler does exactly the same reasoning. This entire function would be, well, the return line, and therefore this entire function, and therefore this entire program would be ub if p is null, therefore p is not null on input, therefore I don't need the check for if p. Again, here is the assembly generated by both versions with and without the if. It is identical, but the interesting thing now is, if you do send a null into this function, it's going to crash, and in the debugger, it will stop at the perfectly correct line if p ++ star p. And you will look at it and say, I'm guarding p. This should never happen if P is null. I wrote, only do this if P is not null. This should never, this line cannot possibly crash. And yes, it will crash right there. So that's the example of undefined behavior tainting, in this case, your entire very small program, but we could have a lot of lines between the if and the return, and as long as you don't change the value of P there, the optimization still holds. So not only optimization behavior made the line where it happened incorrect, anything that follows, of course, is whatever, but now anything before it actually happened in the code can also be basically whatever, just because somewhere down in the program you will eventually encounter undefined behavior. Well, in this case, you would actually never get to that, because your entire program is undefined, and your program will probably crash in a perfectly well-written portion of it, because later you would have encountered undefined behavior. So that's the example of, a very short example of undefined behavior tainting the entire program, including the part before it happens. It travels back in time this way. Now, sometimes you actually want to rely on these optimizations. If you do, you have to be very careful about the underlying assumption. So I'll show you an example where, like, you look at this function f, and while you may know that if P is null on input, it stays null, the compiler doesn't. There are two reasons why. First of all, that P may be alias to a global value. Function G may access the global value. Therefore, after the call to G, P may change. Second, it might actually throw an exception from G, and therefore you will never dereference star P. So in this case, there will be no optimization, and the compiler is entirely correct. This code, even for P equal null, maybe it doesn't exhibit undefined behavior. Another one is very common misconception about consts and optimization. So I'll show it because it's commonly assumed that in this case, so I take my function G takes integer by value, makes a copy of it, and then calls f, which takes x by const ref. And then it returns the result of comparison of x and y. There is a very common assumption that this should be optimized because it must return true. And no correct compiler will ever do that. If it does, it's a broken compiler. Why? It's actually not undefined behavior to cast away const. Unless the object was defined as const, in which case it is undefined behavior, but ours wasn't. Our y was not defined as const, it's int y. So it's perfectly valid to cast away const from object that wasn't defined as const. It's not UB. It may not do what you expect. You definitely don't expect x to change if f takes it by const int ref, but it's not UB. In theory, if I wrote this, if I wrote const int y, in theory, this could be optimized because then it is UB to cast away const. I don't know of any compiler today that actually does that, but that in theory could be optimized. And maybe later some of them will. So how do you look at undefined behavior? Well, okay, necessary evil, you can't change the standard. It's annoying, you should always avoid it. Yes, you should. But it also helps to kind of understand what it's about, because it explains both sort of the seriousness of it, but also the limits of it. Your program is designed and specified to produce certain results for every input, for every valid input, to be precise. And when I say every valid input, this assumes that I also defined what is valid. So what happens if the input is not valid? Well, that's undefined behavior. The user violated the contract. you said that this is the contract. You give me these inputs, which I defined as valid. I'll give you these outputs. You give me other inputs, which I didn't define as valid. I didn't promise anything. That's undefined behavior. That's all there is. So yes, you should define what valid means in that same contract, but if the user violates the contract, it's on the user. Now, why would you ever do that? Well, preconditions or definition of the valid may be very hard to test. So in that case, you would say that certain inputs must be valid, but you would never check for it. And the compilers are in the same boat. Proving that the program terminates in general is impossible, so the standard says, here is my contract with you, the programmer. If the program terminates, I'll give you the correct behavior. If it doesn't, no promises. Now, if you want to be nice to your users, you would also provide validation. Not only you would specify what it means for input to be valid, you would provide tools to validate the inputs. And these tools could be included in the program itself and validate every time, but if the validation cost is excessive, then you could say, okay, here are the optional tools. My main program will go into undefined behavior if the inputs are invalid, and I don't check for it. But here are the tools that at additional cost you can use to check if the inputs are valid. If you want to be good to your users, you should do that in your own programs. Okay, are the compiler writers good to us? Well, fortunately, yes. So the same applies to most compilers. The standard doesn't require it, but the compilers do, and that's the undefined behavior sanitizer, UBSAN. So it's part of both Clang and GCC since like forever. It's getting significantly better in recent results. You turn them on in both Clang and GCC with this fsanitize equal undefined. At runtime, it will report undefined behavior. Looks like this example on the slide. This is the actual output it prints, so it's pretty good. The limitation is it only detects undefined behavior if it happens at runtime. Because now it must do so. Here is this function int g of int k. We all write code like this, and we just don't send large K into it, and everything is fine. The tool should not complain that it might be UB, but hopefully you did check somewhere earlier for valid inputs, but in this code, typically we don't when we write it. So it shouldn't complain that it must be UB unless it actually happens to be UB. So the flip side of it is it relies entirely on your test coverage. So if this code is never executed with a large K, you never get any diagnostic. If there is a code path to get to UB, but you never exercise it, you wouldn't know about it. That's the limitation. So the bottom line, undefined behavior is, you could say, just a program executed out of contract. It's a pretty big just. You should take it seriously, but without over-exaggeration. It won't, end the universe. It won't launch nuclear missiles unless you write a controller for nuclear missiles, but it will make your entire program behave in undefined manner, including some code before that line that may exhibit UB. And I have shown to you how. Remember that definition of your program, the specification, includes the domain. And the domain basically just means the set of inputs that is valid. If you don't have a good reason to define a narrow set of valid inputs, if it doesn't cost you anything, make them broad. That makes you less susceptible to your undefined behavior, because the broader the contract, the less likely it is that somebody will violate it. If you have good reasons to narrow the contract and have tight restrictions on inputs, then of course you do it. Try to provide validation for the inputs, either as a part of the program or as a separate tool. And conversely, when you're writing C++, remember that the people who wrote the compiler were basically guided by the same principle, and they also did provide us with the validation tools, so use them. Thank you. We have a short time for questions, and so maybe just one or two if you have them, and then I can take questions just offline. Okay.
Hi.
Is the mic on there?
Is the mic on? Yeah, the mic's on.
Okay, go ahead then.
Thanks for the talk, Fedor. It was great. What would you say to folks who advise, when dealing with undefined behavior, that we should turn off the optimizer and scrutinize the assembly to make sure the code is defined?
Well, I mean, okay, so first of all, like some of these transformations, like dead code elimination sometimes is done even without optimizer at all. So sometimes it doesn't help. Now, as far as scrutinizing the assembler, well, if you're willing to do it every time, I guess you're fine. Now, in many examples, so I would say it basically places a huge maintenance burden on you. Now, the flip side of it is if you really want to like force a particular way of handling what would have been undefined behavior, you can, and if it's like, it must be really, really important for you to go there, but you can write this piece in assembler. So if you want signed integer increments to be handled the same way, well, if you put add instruction of x86 by hand in assembler, hardware will do whatever it does, and you can find out exactly what it does on your platform. But like for every particular platform, it's well defined what integer overflow does on a given hardware if you execute add. So if you really must, like it's probably easier to write it in assembler than to inspect the assembler. But inspecting the assembler every time, a huge maintenance headache. Okay, the telling me session is over, so just come to talk to me after the